Second.
I feel that. I felt so humble, but now I have to. And be loud.
I'm telling you.
I have to leave it to my
It's gonna be a lot of work.
Alright, good afternoon, everyone. There are still 4 more people who haven't submitted the time slots that they would prefer for the project. So whenever you watch this video, please make sure that you do fill in the survey. It's open till this Friday, midnight, so do that before that. If you don't do it, I'll just assign whatever slot is available from whichever I pick. Right, so please make sure that you fill that out. The 4 of you haven't done it yet. And I will post the slots that I finalize on Monday and make sure that you're in the lab or whatever slot you signed up for. Okay, does anybody have any questions with the homework that was due yesterday, I guess? Okay. So today we are going to continue with our controller design for our motor. So last class we looked at the equations for a DC motor, and we just briefly started looking at how to design the controller, or at least the basics of the frequency analysis in control system, so that we can design a controller. So today's class we will continue where we left off, which was the 5 examples that we are going to be looking at. And so before we jump into that, so some of you who are not familiar with control systems, I think one of you came after class and asked how we got this representation. So if you have some control transfer function of this form, say 1 by SL plus R or something. So what this basically says that if you have some input, which is V of S minus E of S, and you pass it through this transfer function, the output of that is going to be I of S, right? So if I delete this line, whatever input goes in gets multiplied by G of S, and that becomes output OP of S. In control system, typically we will have this closed loop system, either to stabilize this. So in case of our motor example, this is going to always be stable. But let's say I have some scenario where I have SL minus R, in which case that response would be unstable. So either to stabilize the unstable system or to get to a desired reference. So if I wanted to run it 5 ampere and I put some voltage, it might not go and settle to that 5 ampere depending on the operating condition. So I would usually do some kind of closed loop mechanism that will keep updating the voltage so that I can get to whatever current I wanted to go to, right? So once we close this loop, it's pretty straightforward. You can write down the equation. So we have output coming from here. The output of this would be output times H of S. And H of S itself typically will be like some kind of low pass filter. You could have something like omega by S plus omega, commonly used one, or we could have some kind of band pass filter, or we could just have a simple gain. So you might be sensing some current, and your current sensor might have attenuated the signal, right? It might have some gain value associated with it, and you might want to scale that value back up again to the original current that you're passing through the system. Or if you're measuring voltage, one typical way you typically use a resistor divider circuit. So if you're measuring 100 volt signal, your controller can't process 100 volt signal. So you would reduce it to like say 3.3 volts or something, and then measure that value. And then this H of S is basically scaling it back to the original value, right? So that's what it's doing. So any kind of signal feedback processing. So once we have output times H of S, go to this side. The error itself is going to be input minus output times H of S. Input minus output times H of S. And then scale the whole thing by G of S. So G times input minus output times G times H is equal to output. And then once you simplify this, you would end up with this exact same form, right? Collect all the outputs together. So you would have G times input equal to output times 1 plus G times H. And then output by input would be G divided by 1 plus GH, right? So it's nothing too complicated going on here. So once we have our close, so this is going to be the closed loop transfer function, C of S. And we saw that even if we have an unstable system, right? In this case, we have an unstable system because we take the Laplace inverse of that for an impulse input. You would end up with e power 4 times e power 1 times t. Right? For an impulse input, the output will be 1t. So even though you gave a bounded input, the output will be unbounded in that case. So that's a completely unstable system. But once we close this loop, here I'm just closing the loop using a unity feedback. Okay. So H of S is just 1. and I plug it into this equation, I end up with 4 divided by s plus 3. So just by closing the feedback loop, I can make the system stable. So just by looking at what the open loop transfer function is, we cannot make any predictions about the stability of the closed loop transfer function, right? So what really matters for closed loop transfer function stability is the numerator of this term. And what is this term in the denominator? There is 1 plus g of s h of s. Okay, so if I do 1 plus g of s h of s there, this is what I would end up. So this is g of s h of s, right? And 1 plus g of s h of s gave me this s plus 3 and divided. So this would have been 4 by s minus 1, s plus 3 by s minus 1, right? So 1 plus g of s h of s would be this whole term. This denominator itself gets cancelled out to the denominator on the top. So all you're left with is the numerator of the 1 plus g of s h of s term. So if we analyze the numerator term, we can make inferences on the stability of the system, right? So that's what we're going to be doing in this lecture. So we are going to call this numerator function f of s, which is going to be equal to 1 plus g of s h of s. And we are going to look at different scenarios, what f of s can be. And we are going to see what the representation looks like when we substitute different values of s, what f of s is going to come out to be, right? And so today we're going to be doing 5 examples. Does anybody have any questions on this setup that we have? Anybody still unclear with the controls aspect of it? Right. Okay, so we started off with the first example s plus 1, and the port 0 of this is going to be at s equal to minus 1, right? So solve the equation for f of s equal to 0, which implies s plus 1 equal to 0, which implies s equal to negative 1, which is what I marked here. And what we're going to do is we're going to pick a bunch of points that encircles the 0, and then we're going to see what those points map into when we plug it into the f of x plane. So what I'm doing here, Christopher had a different question at the end of the class on Wednesday. So basically, what am I trying to do here? So in our case, if I give you a function f of x, then what would you do? It's some let's say some complicated function of some sort. So we take different values of x, and we try to find out what value of f of x is, and then we plot those values. Of course, this is not the value for the function, but I'm just doing an example. Okay. So we take different values of x, substitute those values, and we get different values of f of x. So this is f of x2, f of x1, f of x3, so on and so forth. In this case, it's pretty straightforward to plot it because it's one real variable mapping into another real variable, right? When we do our s-plane, f of s equal to some function, this in itself is a complex variable, and f of s in turn gives a complex variable. So we end up with a 4-dimensional value. That's why we can't plot it on just a single plot. If I had a complex number and I ended up with f of s being a real number, then again I could have plotted it in a 3-dimensional plane. So I could have chosen the real axis for s, real of s, imaginary of s, and then I could have made this as f of s, assuming it was purely real. Then for different values of these things, I could have figured out what f of s was. Let's say some real combination, some imaginary combination f of s came here. So I would have gotten some nice surface that I could have plotted. But the problem is f of s itself is a 2-dimensional quantity because it has its own real and imaginary component. I cannot plot it on a single plot showing all 4 axes, right? So that's why we are breaking down into 2 axes. One showing the values we choose for s-plane, and then the other shows what it maps into f of s-plane, right? So you could have done the same in a 1D case as well. You could have had just values for x on the 1-dimensional axis, and you could have had values for f of x in the other dimensional axis and said, hey, this one goes here, this one goes here, this one maybe goes here, right? But in a 2D case, since we can visualize it, we put it in the same plot. In a 4D case, we can't, so we are splitting into 2 different plots, all right? We are not doing anything else complicated here. We're just mapping different values of s, substituting into our f of s function, and figuring out where it goes, and then plots it on a separate different plane, right? Okay. So what we are going to do is, given any zeros, we are going to encircle it with some kind of loop, and then we are going to take some discrete set of points and then figure out what f of s comes out to for those discrete set of points. Just for simplicity, I've taken 4 points surrounding it, but ideally you would want to choose numerous points so that you can get a very good map of where it maps into the site. So the four values that I took was 0, -1 plus j, -2, and then -1 minus j. So this is the j axis. And this is the real axis, 1 minus 1. And once I substitute 0, the value mapped out to here. So this one maps here, this one maps here, this one maps here, and this one maps here, right? So what we observed is if we have 0, if we have a curve, a loop that is encircling the 0 in the anti-clockwise direction in the S-plane, then the same loop would encircle the origin in the anti-clockwise direction in the f of S plane, right? Again, we are demonstrating this by a bunch of examples. The theorem itself comes from Nyquist stability theorem, which you can go and look in your controls course textbook, or which in turn comes from Cauchy's argument theorem and argument principle, which would have a much more proper proof, rigorous proof, which does not involve just taking a couple of examples, right? Everybody clear so far what we're trying to do here? Okay, so we're going to look at now a little bit more complicated f of s, which has both a numerator and a denominator. The solution of the characteristic equation of the numerator is going to give us the zeros. The solution of the characteristic equation of the denominator is going to give us the poles. So the zeros are just -1, right? If I substitute this equal to 0 and solve for s, that just gives me -1. If I substitute the denominator equal to 0 and solve for s, that gives me the poles of the system. So the values that I'm going to be choosing, so let me first plot the zeros and the poles. So s equals, so this is the S plane. So this is s equal to -1, and the 0 itself is it's the other way around. So s equal to -1, and the pole is at s equal to 0. Right? So same as before, I'm going to take any loop and just try and encircle the poles and the 0, and I'm going to observe what happens in the f of s plane. So let me pick a value here. Let's say I pick a value here, 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 and here. And then I encircle this. Ideally, again, I should have picked numerous points. Just for simplicity, I'm picking a couple of discrete points. Right, so this one is s equal to 1. This one is plus j. This one is -1 plus j. This one is -2. And then will be the complementary pair, -1 minus j, and then back to 1 again. Right? Can somebody tell me what the value for the first one would be? What is f of s going to be?
2.
2, thank you. So f of s is going to be here. We call this A, B, C, D, E, and F. So A point maps here. Everybody tell me the answer for the second one.
Minus j,
Is it just minus j?
1 minus j.
1 minus j. Okay. So it will be j plus 1 divided by j. J cancels. 1 plus 1 by j. 1 by j is just negative j. So we have 1 minus j, which would be, so what was this? 2. Let's say 1 minus j comes roughly here. Right. And then what would this one come out to? So we have -1 plus j plus 1 divided by -1 plus j divided by j minus 1. This is going to be equal to -1 plus j divided by 2, I think, or -2. So that comes out to, oh yeah, -2. So that comes out to 1 by 2 minus 1 by 2j, right? So 0.5 minus 0.5j. So where would that come out? So 0.5 minus 0.5j, that value would be here. Can somebody give me the answer for this? Pretty easy. Where we substitute -2.
-1/2.
-1/2, thank you. We have negative 1/2. Would it be negative 1/2? Positive 1/2. The reason I doubt it wouldn't be negative 1/2 because it'll put it on this side, which would defeat the whole logic of what I'm trying to do here. So we have A, B, C, D. The rest of the two terms are pretty easy to compute. You can substitute and compute them. But would just be the complex conjugate of whatever the results was in the previous case. Right? So we don't even have to go through the process of doing the computation, but you're welcome to try it. So you have E, then RFS here. So once again, we went in the counterclockwise direction. And here we end up with the opposite direction. The direction itself is irrelevant in this particular scenario. But the point of importance is that we are no longer encircling the origin. Right, so we haven't done sufficient number of examples yet to be able to make any kind of conclusion. But at least one thing that we can observe is the case where we had just 1, 0 and we encircled it with a loop. Then in the f of s plane, the loop encircled the origin in the anti-clockwise direction, same as the loop direction that we chose. If we had chosen the direction to go from A, D, C, and B, then it would have gone from A, D, B, and C on the other plane as well, right? But in the second case, when we had a pole and a 0 being enclosed in the s plane, in the f of s plane, we observed that the origin is not being enclosed, right? So let's do one more example to see if we can see some kind of pattern in what's going on. So the third example that I want to do. So the first one I took only pole, only 0. The second one I took a pole and a 0. So I know when I have only 0, it is enclosing. If I had a pole, it is messing the whole thing up. So I want to explore what poles do on their own. So let me now take an example of where I have 1 by s times s plus 1. Right, without any 0, so that I can just see the influence of poles around. So we have s, f of s. And then in this case, the poles are at s equal to -1 and s equal to 0. Again, the poles are solution to the characteristic equation of the denominator being equal to 0, which implies s can either be 0 or s can either be -1. Right? So we are going to pick the same set of points as before. Enclose them. Right? The same set as whatever I had here. So the only thing is I replace the 0 with a pole, and I'm going to see what has changed right now. So the same set of values, let me just give you the answer. It's a trivial computation. -2, -1, -j, and 1 again. So A, B, C, D, E, and F. So the f of s values comes out to 0.5 minus 0.5 minus 0.5j minus 0.5 plus 0.5j, 0.5, and then minus 0.5 minus 0.5j minus 0.5 plus 0.5j, and then 0.5. So let's see what's going on. We are encircling the S-plane, again same anti-clockwise direction. We are encircling it just once. Now let's see what happens in the f of S-plane. So we initially have 0.5 in the f of S-plane. Then we go to negative 0.5, negative 0.5j. So let's say that's negative 0.5j, negative 0.5. Should have put element A. And then we have point B, which is negative 0.5. And then negative 0.5j. And from there we jump to the complex conjugate pair, which is on the top here. Still negative 0.5, but plus 0.5j. And then we for A, B, C. And then if you look at where point D goes to, we end up back where we started. Right? So we did a loop like this. So we are going anti-clockwise there, but on the f of S plane, it starts to go clockwise. And we end up right where we started within half the data set. So we have encircled the origin once already, and let's continue the process. So we have A comma D here, B comma E here. We go back to this point again. F lies on the same point as C. So C comma F. And then when we come back to the one point again, we end up with the same, right? A or G. That is the same name for both. So we encircle this twice. These lines are overlapping just to show that they're encircling twice. I'm drawing it as two separate lines. So the idea is if you had a pose 0 and you encircled it in the anticlockwise direction in the S-plane, then in the f of S-plane, you would end up encircling the origin in the anticlockwise direction. If you had a pole and you encircled it in the anticlockwise direction, in the f of S-plane, you will encircle the origin in the clockwise direction. So the direction starts to flip. And the other thing is, depending on the number of poles you have, you would encircle the origin that many number of times, right? So let's look at one last example. All right. Save some time. I'll give you the other one as a homework, maybe. You can try and plot it and see what happens. But we have sufficient number of data now to make a conclusion on what's happening. Again, of course, there's not a rigorous mathematical proof that I'm drawing here. So the idea is f of s, let's say, has some z zeros and some p poles. And if we enclose all these poles and zeros in the anti-clockwise direction, right, counterclockwise direction, then we can expect in the S-plane, then we can expect in the f of S-plane we will encircle the origin in the counterclockwise direction again by the number given by the minus p. So if I had so if I had a case where I had more than the two poles that I've considered, two poles or 2 0, 1 pole 1 0 case I've considered, let's say I have a whole bunch of zeros. Right? If I have, let's say, this, and I take a loop, some odd looking loop, doesn't matter what the structure of the loop is, and I enclose this in the counterclockwise direction. In the f of S-plane, can anybody quickly tell me for the case that I've drawn, how many times will I encircle the origin and what direction I'll encircle the origin in?
2 times clockwise.
Okay, so we have 1, 2, 3, 4 number of poles, right? And then 2 number of zeros. So the difference is -2, -2 in the counterclockwise direction. So it will end up being clockwise direction in the f of S-plane. So you can take any kind of example and try this out. Just put like a random set of poles and zeros in MATLAB and take a bunch of loop or a circle around it and try and map it into an f of S-plane, and you'll see that no matter what you do, it will end up coming out in this particular form that we have. Right? Can I have a transfer function that can be modeled using the diagram that I've shown there? Can I get a transfer function with these number of poles and zeros that I've shown there? No? Why not?
Has to be symmetric across the
Okay.
x-axis.
So whenever I have all of these poles and zeros that are off axis would be complex conjugates, right? Because if they are not, the reason these poles come out complex conjugate is if you have, let's say, LC network of some sort, right? So your denominator would be a square plus LC. And then the inverse of that would be a square is negative LC, right? So you have plus or minus JLC. You cannot get just one J alone, which would indicate that your system itself has some kind of complex number, which is not possible in real world system, but you can create mathematical systems that have those properties, but not real world actual systems. Okay, so everybody clear on this part? If I give you some kind of FOS transfer function, which has some Z zeros, Z poles, and if I give you the, you should be able to figure out where the poles are, and then depending on what loop you draw, you should end up having some kind of curve on the FOS plane that encircles the origin by now number given by this. Let's say the same loop. What would happen if I encircle it like this? Would the numbers still be the same for the encirclement of the FOS plane, or would it be this by a factor of 1? Will be reduced. So this again is only applies to the, or you can choose any loop that you want, and it only applies to the poles and zeros within that loop. To get an idea, rough idea of what the Cauchy argument principle proof would do is if you draw a vector from here to any point on the loop, and as you go around the loop, this vector would complete a full 2 pi degree, right? That is what is mapping into a circle on the other side. If you had a pole outside and you had a vector, as you complete this full loop, it never goes 2 pi, it never actually exceeds this angle, right? So it goes from here, goes positive, positive, negative, negative, and comes back to 0. So that's the reason it doesn't end up enclosing the origin. So when you map this vector onto this plane, just for that particular loop alone, you would end up having some kind of loop that would end up looking like this, right? It wouldn't go through the origin, it wouldn't enclose the origin. But if you had something within it, whenever it does the full loop, it does the full 2 pi, so it would end up being a circle on the other side, right? That's all the whole proof is in essence. Okay, so let's try and see if we can figure out stability of a system. Yep.
Could you explain again why it was clockwise instead of counterclockwise on the previous exam?
Oh, in this one?
Yeah.
Right, so the rule is, if you remember in the case where I had the transfer function s plus 1, right? This was just a 0 alone. And if I encircle the s equal to minus 1 in the anti-clockwise direction, and therefore s plane, I encircle the origin the same number of times. When I had the poles, the third example, when I had 2 poles, I encircled the origin twice, and the direction also flipped. In the s plane, I still went anti-clockwise direction. But in the f of s plane, I ended up in clockwise direction two circles, right? So the idea is if I have some z zeros and I go and encircle all those zeros in the anti-clockwise direction, I would end up having z circles in the f of s plane encircling the origin in the same direction as what I chose to loop here. If I had some p number of poles in the s plane and I encircle it in the anti-clockwise direction once, then I would end up with p number of circles encircling the origin in the f of s plane, but in the opposite direction, right? When I have a combination of these two, which is what I did for example 2, where I had a pole and a 0, there is whatever this is creating, that is going to cancel that out, right? So in effect, what is left is the difference between the zeros and the poles. So in our case, we had 2 zeros and 3 poles. Did I have 4 poles? Sorry. Right? The loop we considered initially was this whole thing. So I have 4 poles here, 2 zeros. So substitute the values here. 2 zeros minus 4 poles, you end up with -2. Right? So -2 in the anti-clockwise direction is the same as saying 2 circlements in the clockwise direction. Right? Any other questions? Yep. Jonah.
If we have the same number of poles and zeros, then we don't circle the origin at all, right?
Yep, we don't.
But do we know like where exactly the circle will be placed?
It depends on what you choose your loop to be.
Okay.
Right? Because it is depending on whichever loop you choose, the way the circle comes out on the other side will change over.
Got it.
Right? It's basically the distance between whatever the net distance. So if you had, let's say, a pole and a 0, and you had some kind of encirclement, whatever this angle, vector angle is being given by this is going to get somewhat cancelled out by whatever this angle, whatever this angle is giving at that point, right? So it has like a counter effect on whatever the other one is trying to do. It looks as if this is actually adding, but remember that this is in the denominator. So if it is along the same direction, the vector is actually subtracting the angle out. Okay? So where it would end up, that would depend on the loop you choose. It can't have a specific value. Yep, Christopher.
Can you go back to what is like the significance of f of s, that system on the left? I think you wrote like it was the numerator of that.
So this is f of s. 1 plus g of s h of s. That is f of s. And then, so when I say the numerator of f of s is what matters. So when I had this example, it's a little bit confusing. When I had this example 4 by s minus 1,
yeah,
this is the g of s, this open loop transfer function, right? When I put it in the closed loop form and I substitute into this equation, I would have 4 divided by s minus 1 divided by 1 plus g of s h of s, which should have been s minus 1 plus 4 divided by s minus 1. Okay? Because this is 1 plus h of s g of s. This is 1 plus 4 divided by s minus 1. So if you look at the denominator of 1 plus g of s h of s, it actually cancels out with this denominator here. So that's why that term actually doesn't matter in the closed loop system at the end of the day. Right? So it's the numerator term that contributes. Because this is what ends up becoming the, so if you look at the full transfer function c of s, it would be 4 divided by s plus 3. Where did this s plus 3 come from? It came from the numerator term of 1 plus g of s h of s.
So s plus 3 is the f of s then, or?
S plus 3 is not f of s. The numerator of f of s is s plus 3. So f of s itself would be this whole term.
Oh, okay.
Right? F of s would be s plus 3 divided by s minus 1. Because what is f of s? F of s is 1 plus g of s h of s.
Okay, sure.
You're saying that only the poles and zeros of the denominator of the closed loop system is what you're considering here. Is that correct?
Yep.
Why?
Poles, no, I'm not considering the poles and zeros of the closed loop system. I'm considering the zeros of the denominator of the closed loop transfer function.
Yeah.
That's the only thing that would determine stability.
Do you have an intuitive explanation? Sorry if you already covered this, but do you have an intuitive explanation for why you don't have to consider the numerator in the closed loop transfer function?
Oh, we do the numerator term does not contribute to the stability. Right? So let's say I have so this factor for the reason for stability comes from, let's say I have, let me pick some example that I can factor out. Or some factor.
Sure.
I don't know. So you'll get some coefficient here, some coefficient B, right? And when I take the Laplace inverse of it, it will just be e power negative 2t plus b e power minus 3t. Okay. The stability is determined by whether this coefficient is positive or negative. The numerator part never played a role in the coefficient. It plays a role in the scaling factors a and b's. It never plays a role in the coefficients themselves. So stability comes from the fact that the denominators have terms such that the roots of this denominator term are all negative. Then in this case, the inverse Laplace would give you e power negative coefficient terms.
Yeah.
And you would have a stable system. The zeros do play a role. So for instance, if you had a system, let's say you had a system without a zero and your response looked like this. If you had a zero, you would typically get a response that pulls it a little bit downwards. Right, so it would change the characteristic response because these coefficients do affect how the response looks like, but it does not change whether they would converge or not.
Sure, but the zeros in the denominator are the poles of the closed loop system.
Yep, the zeros in the denominator would be the poles of the closed loop transfer function. So the zeros of the denominator matters.
And not the poles, because there should be no poles.
Not the poles. So the poles of the denominator won't matter because the poles of the denominator would cancel out the poles of the numerator in the closed loop system. So going back to this example, right, the poles were s minus 1. And here also the s minus 1, those two terms just cancel out.
Yeah, so once you simplify, you shouldn't have any poles in the denominator, correct?
or denominator, poles of which closed loop or f of s?
You should not have any poles, all the poles of the closed loop transfer function should be in in the denominator. Correct?
All the poles of the closed loop. By definition, poles are something that happens on the
That's what I'm saying.
denominator.
That's why it's of interest. That's what you're saying. Is that correct?
Could you repeat it? Sorry.
That is why the denominator of interest is because the poles are there.
Yep.
Okay.
Oh, yeah, okay. So yeah, we are interested in this part because this is where the poles reside. Yep. So, Ben, did you have a question? No.
Just small follow-up. So, I mean, in this case, it was like 4 where s minus 1, the s minus 1s cancel. Does it have to be s minus 1? Like, do they have to be symmetric all the time? Such that like the denominator of the denominator cancels with the denominator of the numerator.
Oh, that's just because I don't have to take any particular example of any sort, right? Like I could have, let's say G is just some numerator divided by some denominator. Once I plug it into the formula, the D's would cancel out by the nature of them. So you have numerator by denominator times denominator plus numerator divided by denominator. Okay? It has nothing to do with the transfer function that I chose. It just has to do with how fractions work in math. Okay? So the denominator does end up expressing itself as part of denominator plus numerator. Okay? But the terms themselves they cancel out. Okay? Any other questions? So let's try and see if we can infer some stability from our f of s plot. Okay, so let's say I give you some complex transfer function as a plot of the poles and zeros in the S plane. And if I give you this plot, you should be able to figure out what the transfer function is, right? Pretty straightforward. Let's say there is a pole here, there is a 0 here, and there is some pole here, and let's say there is some 0 here. Is this system stable or unstable? What was it? Unstable. Why is it unstable? Poles in the left half plane. Is there a problem though? Shouldn't the poles be in the left half plane? Because you want the negative term in the exponent, right? E power negative alpha t. So let me ask for 3 different cases. Let's say this represents a transfer function g of s in the case 1. Let's say that the same diagram represents the transfer function 1 plus g of s h of s. And let's say the third case, it represents the closed loop transfer function, which is g of s divided by 1 plus g of s h of s. Okay, let's start with the simple one. Let's say the diagram that I've given here represents g of s, the open loop transfer function. Is the open loop transfer function stable or unstable? Do you want your poles to lie on the left half of the plane or the right half? Do the zeros matter for the open loop transfer function? No, right, that's the example I just gave. The zeros just end up as coefficients multiplying the e part term, so they really do not matter. The poles do matter, and it matters whether the poles are on the right half or the left half. When I tell you they are on the left half, that means, let's say, let's go back to the example that I've drawn there. Let's say this is s minus 2, and this is s minus 3. Okay? That's how I end up with the denominator s plus 2 times s plus 3. And we just saw that was a stable case. Right? So as long as I have poles on the left half side of the S plane, it's perfectly stable system. Okay? Let's do the third one, the again simple one. Let's say this system represents g of s divided by 1 plus g of s h of s. Is the closed loop system stable? It is still stable, right? Same logic, because we have s on this side, completely fine. Let's now say that this plot actually represents 1 plus g of s h of s. And I want you to infer the stability of the closed loop system. So is C of s, which is g divided by 1 plus gh, is this stable or unstable?
It's unstable because the 0 on the right half plane would become a pole.
Perfect. So the 0 that's on the right half plane would end up becoming the pole for the closed loop transfer function. Right? So if our f of s, this term has a 0 on the right hand side, this ends up actually becoming the pole of the closed loop transfer function. Alright, so we cannot have any zeros on this, on the right hand side. Can we have poles? Can I have a pole on the RHS? Let's say again the same case, 1 plus d of s h of s, but I had a pole here. Is the closed loop system stable or unstable? Instead of the 0, I had a pole there. Is the closed loop system stable or unstable? Stable, perfect. Right, so because this again goes to the denominator, the poles of this do not matter. The zeros of this becomes the poles of this closed loop transfer function, and that's what would determine stability. So what we can say is that looking at this plot, for 1 plus g of s h of s, we can say it shouldn't have any zeros on the RHS. We are not interested in the stability of 1 plus g of s h of s by itself, right? It has absolutely no physical meaning or any use to it. Because what happens is this is just the denominator term of the closed loop transfer function that we are interested in. Yep.
Sorry, I just wanna make sure I understand. So if there are zeros on the right-hand side and they're not directly on the axis, that still matters because then they'll turn into poles, which will then be both negative or positive and complex.
Oh, if I had a 0 here, you mean?
Yeah,
Oh yeah, this would still matter. That would still make it unstable.
okay,
Right, because you would end up with a term s equal to say 1 plus or minus j. Right? The plus or minus j term would end up coming out as cos and sine components. This one term would still end up being e power 1t times sine omega t. Right? When you take the Laplace inverse. And the time response for that would end up, instead of being a nice exponent that we would expect, it would be a sinusoidally exponentially growing signal. It doesn't help for stability either. Yeah, it doesn't matter if it's on the x-axis or if it's above. Anywhere on the RHS, if there is a real component, so only the real component matters. If there's a real component anywhere on the RHS, that would blow up the whole system. Yep, Joe.
It could be stable if there was like if it was canceled out, right? Like if there was a pole or a 0 in g of s that canceled out that pole, right?
Oh yeah. If you had one right on top of it, those terms would just cancel out. Right? It is a little bit tricky. Let's say you have an inverted pendulum and it had this characteristic where the open loop system had some kind of pole on the right hand side. And if you try to cancel it out with a 0, you better match it exactly.
Yeah.
But that would not be practical in a real world system. Even the tiny difference, it would still make it unstable. So if I had 0 here and the pole was just slightly off, a little bit, doesn't even matter, 0.0001 e power minus 20 or 30, that would still make it completely unstable, right? Only in math, we can cancel those out nicely. In reality, that wouldn't be feasible. Any other questions? Yeah.
So pole 0 cancellation is never used in the real world?
Oh, we do use them, but the reason we use them is not to stabilize it. We would use them in, let's say we have a pole very close here, right? Then we would typically use a 0, place it close to it, so that the effect of it is subsidized, right? But if it's on the right hand side, there is nothing you can do to cancel it out and close. You need to put some kind of different controller to be able to stabilize it, right? Yeah, these pole 0 cancellation typically you would do when you design like a closed loop control for a buck converter or something, right? You want a better phase performance, so you want to put all the poles far away. So the only thing you can do here is use a lead lag compensator and cancel out the poles very close to the y-axis. Yep.
1, 2, and 3 are all transfer functions.
Yep, 1, 2, 3 are all. This is the transfer function of g of s. This is the transfer function of 1 plus g of s h of s. This is the transfer function. Any questions? All right. So this is a condition, should not have any zeros on the RHS for stability. Okay. So now what I'm going to do is, we are not going to have any zeros here on the RHS. That is all. But let's say I take a loop which encloses the whole RHS plane. And let me go anti-clockwise again. So this goes all the way along the negative j omega axis and then has an infinite radius. So this is some r e power j theta, with r being infinity, r tending to infinity. No math people will hate it, but I'm fine with it. So it's a loop that encloses going all the way to infinity and then comes back around the plus j omega axis. And then goes around along the negative j omega axis and completes the whole right hand side plane, right? If I take a loop like this and I evaluate it at different points, what will my loop in the f of s plane look like? Will it encircle the origin? So previous cases I took like nice loops which had like 4 tiny points and so on and so forth, but now I'm just going to consider a mathematical loop that's infinitely large. It never encloses anything on the LHS. It encloses everything on the RHS. Well, when I map each and every single point here to a equivalent point on the f of s plane, will it encircle the origin? Will it not? How many of you say it won't? How many of you think it will? You say yes. How many of you think it will enclose the origin? Sorry? Anybody tell me why it will enclose the origin? What was the condition I gave? I said that it wouldn't have any, so we clearly know that there shouldn't be any zeros on the RHS. Right? That's the condition I laid. But I never said this doesn't have any poles on the RHS. Right? So I could have any number of poles on the RHS. Let's say the number of RHS poles are 0. RHS poles equal, RHS poles equal to P. How many times will this encircle the origin? What was it? P times in the clockwise or anti-clockwise direction?
Clockwise.
Clockwise. So if you had zeros there, it would have encircled in the anti-clockwise direction. And I've already said it can't have any zeros. If it had, the system is unstable. There is no purpose even analyzing the system. Right? We are trying, because we started off with a stable motor. If we design a control system and make it unstable, then we are just bad designers. Right? So we are going to design a system that doesn't have any zeros on the RHS. Now we are going to see what would happen if there are any poles on the RHS. Well, if there are any poles, then it would encircle the how this curve forms. And the number of times it encircle the origin in the clockwise direction would be equal to P. Right? Everybody clear so far? It comes.
So if you can draw any arbitrary circle on the S plane, how does that transfer over if you could encircle any arbitrary number of poles and zeros for any transfer function? Like what does it actually mean when we're circling something? Like, is that only for analytical use, or does the circle that we're drawing actually mean something?
No, it's just a purely analytical use. It has no meaning to it. It is just that I want to map everything on the RHS. Whatever is on the RHS, I want to capture it here.
Okay.
Because the trouble is things that are on the RHS is what causes us trouble. We don't care what happens on the LHS.
Okay.
LHS would determine what the response. If I had a 0 here, my response would be quite oscillatory. If I can cancel the pole and push it farther, then I could get a little bit more stable response. So this would determine how nice the response looks like, but it does not determine the stability.
Okay.
The only things on the right hand side are the one that's troubling, because it will determine whether it looks like this or whether it looks like this. Okay, so this is what we are trying to differentiate. And the only way we can differentiate is because it doesn't matter whether I have a pole 0 very close to the y-axis or 0 very farther away from y-axis. If it is very close to the y-axis, it will take a very large time to blow up. If it is very far from the y-axis, it will take a short time to blow up. But either way, it's unstable for me. Right? So this is just a pure mathematical consideration. We are considering this whole loop so that we can, or another way of saying is I'm just considering everything on the RHS plane. Okay? Any other questions? Okay. Everybody clear so far? So if we had some poles here for the 1 plus g of s h of s transfer function on the RHS, then our system is absolutely fine, our closed loop system. But if we had any zeros for the 1 plus g of s h of s transfer function on the RHS plane, our system becomes unstable. Right? So whenever we do this mapping for this infinitely large loop on the RHS plane into our f of s plane, we should make sure that there is no anti-clockwise encirclement, right? Just based on this, can I tell if there is no, so let me say the other way around. If I give you this plot, can you tell me the number of poles and number of zeros in the S-plane? Right hand side S-plane? Is the reverse mappable? Like if I, so from here I can tell, yeah, so this would be number of clockwise encirclement would be P minus Z. And if I give you this number, can you tell me what P and Z are? Not at all, right? Because there are two variables here. If I tell you there are no zeros, then you can tell me the number of poles. If I tell you no poles, there are number of zeros. But just by looking at this graph, you can't tell the reverse of what is going to be happening there, right? On the RHS plane. Okay. So again, for our case, no. 0 equal is it Z equal to 0, and this is for 1 plus GH transfer function, right? So if this is satisfied, then C of S is stable. Closed loop transfer function is stable. Okay. But then we have this problem where we have some kind of encircling in the origin. It's not a problem in itself, but it encircles the origin P times for this particular situation. What can you tell about the P? If I give you G of S, can you tell me what P is? Let's assume H of S is just some unity game. Can you tell me what P is going to be if I give you G of S? What is P? How does this P link back to our G of S transfer function?
It's the zero minus the poles.
Right, so let's look at let's go back to our numerical example again. So we had 4 divided by S minus 1. Once I plug it in, our C of S was 4 divided by S minus 1, and our 1 plus G of S H of S was ended up being S plus 3 divided by S minus 1. Oh, well, in this example, what is the pole of the 1 plus G of S H of S? What is going to be the, in this particular example that I've written here, what is the pole of 1 plus G of S H of S?
S equals 1.
S equal to 1. Again, poles are solution to the denominator, right? So so this whole thing is F of S. Okay? This whole thing is 1 plus G of S H of S, which we are going to be calling as F of S. The zeros are the solutions to the denominator, sorry, numerator, and the poles are the solution to the denominator. So we already saw the 0, 0 luckily is not on the RHS plane, because if this had S minus 3, then the whole thing is done. It's a closed loop unstable system, because you have 4 divided by S minus 3 and the system blows out. But since we have S plus 3 on the denominator here, we are absolutely fine. We have a stable system. But then what can we tell about, so given any 1 plus G of S H of S, and if I ask you for the poles of it, how does it link to G of S poles or poles G of S zeros? If I give you a transfer function, can you instantly tell me what the poles of the 1 plus G of S H of S is going to be? Okay, it's going to be the same as the poles of the open loop transfer function. Yep, sure.
Is that always the case or only for like constant value of H of S?
Only for H value being a sum gain, right? Yeah, some kind of constant. If the H had some other thing, then that would come into picture. Okay? Most of our cases, our H of S will typically be some kind of scaling factor, just for like current sensor or voltage sensor, whatever be it. But yeah, it's only applicable when this doesn't have. Or in the other case, you can, if you have H of S as some transfer function, you can say that the poles of 1 plus G of S H of S is same as the poles of G of S H of S. Right? When H of S is equal to some gain, it's just the same as the poles of G of S. Right? Very clear so far. So this will be number of poles of F of S, which is 1 plus G of S H of S, is the same as number of poles of G of S, right? Very clear so far. So two things that you need to take away from this. If our closed loop system is stable, there better not be any 0 or 1 plus G of S H of S on the RHS plane, right? Z equal to, so this is 0 on the RHS plane. This is poles on the RHS plane. So number of poles on the f of s in the RHS plane, doesn't matter what plane, it's always true, with respect of it's on the left hand side or right hand side, it's going to be equal to the number of poles of g of s, right? And the number of times we encircle the origin for an infinitely large loop enclosing all of RHS in the s plane would be equal to the number of poles. The number of times it encircles the origin would be equal to the number of poles on the RHS for either f of s or g of s, which is exactly one and the same. Very clear so far. Okay. In our case, we have a very special nice system where our system is open loop stable. Right? If you look at the transfer function 1 by SL plus R, 1 by SJ plus B, they have all the property that the poles are all on the left hand side. There are no poles on the right hand side. For all the systems that we are going to be analyzing throughout this course and even an advanced electric drive course, you would always see that the system is very nicely conditioned, that they are open loop stable. And if I have a system that's open loop stable, what would happen to, how many times would this loop encircle the origin in the f of s plane? What was it? 0, right? Because the number of times it encircles this origin is equal to the number of poles on the RHS. If our open loop system is stable, then there are no poles on the RHS, right? At least g of s has no poles on the RHS. That means our f of s also has no poles on the RHS. So for our stable system, this is what we are gonna make some observation. If system open loop stable and system closed loop stable. So what does open loop stable mean? If our system is open loop stable, then g of s has no RHS poles, which also implies 1 plus g of s h of s has no RHS poles. If our system is closed loop stable, that implies 1 plus, or let me put it the other way around, our closed loop transfer function c of s has no RHS poles, which is same as saying our 1 plus g of s h of s has no RHS zeros. Right? Notice that these two terms change because the closed loop poles of the closed loop transfer function is same as the zeros of the 1 plus g of s h of s transfer function. Right? Everybody clear so far? So we are always going to be considering systems that are open loop stable, and we want to make sure that the system is closed loop stable. What this then tells us is, if I picked an infinitely large loop, and so if I say that it's an open loop, so the first line tells me that there are no poles on the RHS. So those are gone. So there are no x. The second one tells me there are no zeros. So there are no x's, there are no zeros here. If I draw a very large loop and encircle everything on the RHS, there is absolutely nothing going on there. So what I'm going to get is some kind of curve. Typically that would look like this kind for first order system. But if you see, it will never enclose the origin. Right? So just by looking at the f of s plot, I can instantaneously tell for a loop that encloses everything on the RHS, I can immediately tell whether the system is stable in the closed loop or not. Right? Everybody clear so far? Okay.
Can you be closed loop stable without being open loop stable?
Oh yeah, that's the example that I have right there. 4 divided by s minus 1, open loop unstable, closed loop absolutely stable. Inverted pendulum case, right? You have something, this is unbalanced, but I can balance it. I'm very poor at it, but you get the idea. Okay, any other questions? Okay. So I have one pesky little problem here. Evaluating this 1 plus g of s h of s. Now, this is very easy if I give you like an example case where I had 4 divided by s minus 1, and then if I had to do plus 1, simple, straightforward, I can solve this, and the roots are s plus 3 and s minus 1, sorry. Let me say if I had something more complex, s power 4, s cube plus 1 divided by s power 6. S squared plus one or some, or let me say the denominator I've given you in a nice. Right? So if I given you in this nice form, and then if I ask you to do 1 plus, and then solve it, it gets a bit more complicated to solve this. So just to make our life simple, what we are going to be doing is we are going to redefine. Let's say we have some k of s. Right? K of s, we are going to redefine it as f of s minus 1. Right? That's all we are doing. And what that helps us then mean is that we don't need to do this one addition to g of s, h of s. So that is just g of s, h of s. Right? Why am I doing this? Because I don't want to take the denominator, multiply with this, which is just multiplying with 1, but then add the denominator term with the numerator term and try to bracket to separate out the coefficients again, which becomes a somewhat of a complicated problem. Because typically when you have a complex system, you won't have those nice equations. Like in a typical industrial system, what you'll do is you will take a frequency analyzer, put different frequency sine wave signals and look at how the response looks like. And depending on the slope of the response, you would get different kind of responses. And we'll get to Bode plot in a minute, but you might have plots that look like this. Right? Just by looking at this response, I can tell you exactly where the poles and the zeros are. Right? So it has a pole here, and if it's going at 20 dB per decade, that's a first order pole. So if this is alpha, I have a pole at alpha, and then here it becomes flat. So there must be a zero there, s plus beta, and then here again it's falling at some gamma, s plus gamma. And then here it starts to fall at 40 dB per decade. So that must be a double pole. Right, so it's pretty straightforward to tell just by looking at the frequency response what the poles of a system is. So this is how typically you will get for an industrial system. You pass different frequencies and figure out what the transfer function is. You don't typically have a nice mathematical expression. So if this is what g of s times h of s is, and then if I tell you, hey, add this to 1 and then factor this out again, it will be quite complicated. If it's just a fourth order transfer function, then it's pretty easy. If it's fifth order, still their analytical expression. Higher order, you just can't solve it by hand. You need some kind of numerical simulation to figure out the roots. Why complicate our system unnecessarily? If we can just analyze directly g of s, h of s, we already have a form. We don't need to refactor the roots again, right? So that's the idea for just keeping it as k of s. But then what happens to, if this is my plot of f of s, what will be my plot of k of s? How will it look like?
Like the same thing shifted.
Perfect. So every single point, I'm just subtracting one out of it, right? So I'm subtracting 1 out of this, subtracting 1 out of this, subtracting 1 out of this, 1 out of this, every single point. And here, whatever was, I'm subtracting 1 out of it, right? And my 0, which was here, now should come here. So whatever curve I had here, this would be my new curve, K of s. Right? Whatever I had before f of s curve, all I had to do was just shift it backwards by 1, every single point. And I get the k of s curve. And the advantage of looking at k of s is I don't have to refactor the roots again. Right? And now my condition though is, if you look at this, now the k of s is actually enclosing the origin. Then that is not a fair comparison for stability though, because my origin again was shifted by 1. Right? So the condition now is my k of s should not enclose minus 1, or typically in control system, they would say it is minus 1 plus j0. Right? No encirclement. Of minus 1 plus j0. Right? If my curve does not encircle this point, then my system is stable. Everybody clear so far? There is no magic here. I just took the 1 out just so that I can make the system simple without having to refactor the roots out. Okay. Now, let's put some constraints on what our system is going to look like. We already laid out a couple of constraints. One constraint. So we want our closed loop transfer function to be stable, which is obvious. Second thing, our open loop transfer function g of s is also stable for the systems that we are analyzing. This is not This is something that is required for any system that you would design, unless you want to design like a museum piece for a chaotic demonstration or something. But otherwise, for any practical system, you would want it to be stable. And this is required. Happens to be so for all the motor cases that we have, that our open loop system is perfectly stable. The third constraint is again something that happens for motor control system and for most real world systems, that the order of the denominator is greater than, not just greater than or equal to, it's absolutely greater than order of numerator. Right? So what does this mean? I can have transfer functions that look like this. Right? This is okay. I can have s plus 1 divided by s squared plus 3. This is also fine. But I cannot have this. Alright, so this is a no-no. Can somebody tell me what is the reason I don't want to have this, but these two are okay? What am I trying to get to? So let me give you a hint. When you studied the Nyquist, so whatever we have there is basically the Nyquist stability criterion that I've written down there. Whenever you studied it, at some point your faculty, the teacher would have mentioned that this is exactly the same as Bode plot, right? But that is only true for the third condition. In the diagram that I've drawn there, loop that I've drawn there, which part of it represents the Bode plot? If I give you a transfer function, how do you get the Bode plot? Don't tell me Bode of some function in MATLAB. How do you do it by hand?
Just the y-axis, right?
Just the y-axis, perfect. So all I have to do is go around and pick points on the y-axis. And what is Bode plot? Whatever transfer function I have, let's say I want the Bode plot of g of its transfer function. It is basically the steady state response. So g of j omega. So if I had some transfer function and I give a sinusoidal input to it, the response would actually look like this. There would be some exponential component that decays and then settles down to a nice sine wave. Right? The Bode plot is only interested in what the steady state component of the sine wave is. Right? The exponential component is given by the real part of the root. So you have alpha plus j omega. The exponential part is given by the real part of the root. The imaginary part gives you the sine component of it when you do the Laplace inverse. Right? So Bode plot is basically saying, hey, I don't care about what happens to the exponent. I will give some sine wave to my system, and then I'll wait for quite a bit of a long time so that the system stabilizes. And then I will look at what the magnitude of the output is and how much is phase shifted from the input. I will take that as one value. And then I will go to a next higher frequency, do the same experiment, find out what the magnitude is, what the phase is. Right? And if I plot all the values of the magnitude at different time instants, that's exactly what I've drawn here. For a complicated system, that's what the Bode plot would look like. At different frequencies, I go and look at what the magnitude was, and that's exactly what I plotted there. Right? So that's the magnitude at steady state. So it's basically saying what is g of j omega, ignoring all alpha components, which is the transient exponential component. And what does this represent here in this axis? It's basically this axis. This is negative j omega, this is the positive j omega. Right? So basically this vertical axis that we have here, every single point you substitute and find out what f of s is, right? And whatever the curve comes out, if you take the magnitude part of the curve and the angle part of the curve, you get the Bode plot in a sense, right? Now, if the order of my numerator is lesser than the order of my denominator, when I pick a loop, right, what happens to this very large loop that I've chosen? If the order of my numerator is lesser than the order of my denominator, what happens to the very large loop that I've chosen, just the semicircle part of it alone? Let's substitute. Let's look at an example, right? Let's look at the case. Let's look at s plus 1 divided by s squared plus 3 case, right? So that very large loop is given by my equation r e power j omega. R e power j theta for different values of theta going from negative pi to positive pi. And then we have 1. And then again, s is different values, r e power j theta, the whole square, plus 1, plus 3, sorry. Right? Again, this r e power j theta, that's just an expression, right? Because there's going to be some real component to it, some imaginary component to it. The real component is going to be cos theta, the imaginary component is going to be j sin theta from Euler's equation. That's exactly what I'm representing in this compact form. Nothing too fancy there. As this r goes to infinity, what is going to happen to this term? Which one grows faster? Is it the numerator or the denominator? Denominator.
We'll go to 0.
Okay, so this whole thing goes to 0 as r goes to infinity. Right, so as r goes to infinity, this term goes to 0. Does it always goes to 0 for all transfer functions? For what kind of transfer function would the term go to 0? Okay, so whenever you have order of the denominator greater than the order of the numerator, the denominator goes towards infinity much sooner than the numerator. So this whole system goes to 0 as this r goes to infinity. Right, so that's the reason we put this third constraint. There is nothing within Nyquist itself that limits, that requires us to put the third constraint. It is just for this case so that we can now say that every single point on this loop, when I map it into the f of s plane, what will it map it to? Every single point on the semicircle in the s plane would map into what in the f of s plane? What did I do by substituting s equal to r plus rj theta there? That was basically just taking every single point as theta varied from negative pi to plus pi. I was just going around every single point on the semicircle. Right, and irrespective of what the theta was, it ended up being that the transfer function became 0. And the transfer function is basically f of s. Right, so if I go around this and pick every single point, basically varying my theta, all of them maps into one single point which is 0. Right? So all those points would just become a single point. So this is my point for stability. That is 0. So all of those points map into this one, r e power j theta, with r tending to infinity, if order of the denominator is greater than order of the numerator. Right? In this itself, if I plot for different values of omega, that will give me some kind of curve like this. And what about the other one? If I have the graph for this, how can I get the graph for this one, negative j omega? What will it look like?
Just the symmetric version.
Perfect. So whatever graph I have here, so this will have looked like some waveform. It will just be the same one with the symmetric nature, right? Because it always appears as complex conjugate. If I have this here, j omega, this is the complex conjugate negative j omega. So whatever plot I got here, this was for f of j omega. And this plot would have been f of negative j omega. Right? So when I go to the f of s plane, I don't need to do any of this. All I need to look at is just the curve that I get for f of j omega alone, which is exactly the same as what plot? If I give you the transfer function of some system and I ask you the plot of the transfer function j omega, what is the plot? Bode plot. What is the Bode plot? For different magnitudes and different frequencies. And our requirement is, let me just take 3 more minutes. The requirement for me is, whatever plot I get here, it should not be in such a way that it goes and encircles as -1 plus j0. Okay? So if I had a curve that looked like this is absolutely fine. If I had a curve that looked like this is absolutely fine as long as -1 plus j0 is far out. If I had a curve like look like this, that encircles -1 plus j0, then we run into trouble. right? Because this is only one half of the plot. So let's say this is the plot you get. The other half is for g of negative j omega, which should come out as the complex conjugate of this. So when you plot the whole plot, you have seen that you would get a negative 1 plus j0 encirclement. If you had something like this, then that wouldn't happen. Right? It will encircle something, but it's not negative 1 plus j0. So the requirement for stability is all I have to do is look at the Bode plot, and my graph at no point should it enclose the negative 1 plus j0. So let's say my Bode plot comes out like this, and I have some magnitude plot that looks like this. Let's say the boundary condition where we just touch minus 1 plus j0. Right? This is the boundary between stability and instability. If I look at the magnitude of this, what is that going to be? Let's say this is the magnitude of f of j omega. How would that magnitude be in the Bode plot? Thank you. So this is just going to be 1, right? Because that vector is basically going from 0 to negative 1. The magnitude would have to end up being 1. So if I have a magnitude of 1, what does it come out in Bode plot? When I take the logarithmic of it?
0.
0. So that is going to be the 0 point. And what is going to be the angle of this vector?
180.
180 degree. So because if I had a vector in this direction, it's 0 degree. If I had a vector here, it's 90 degree. If I had a vector here, it's 180 degree. So if I look at the plot where that crosses over, and if this is 180 degree or negative 180, both same, then that would be the condition for in between stability and instability, which we would qualify it as unstable, right? If for this case, it would be such that where the magnitude of the log plot is 0, our phase plot would be far away from 180 degree, right? There's going to be some kind of margin. So if you look at this, where the magnitude of this vector is equal to 1, right? If there was an enough delay in the system that it gets rotated a little bit leftwards, then it will become unstable. This difference is called the phase margin between how far away it is from becoming unstable. If it is fully enclosing it, then there is no phase margin. It would just be below 180 degree, which makes the system unstable, right? So from next class on, when we derive on Wednesday, when we derive the PA controller for the motor, we are going to be talking in terms of phase margin. So how much margin we have from the system becoming unstable. If the margin goes to 0, the system becomes unstable. If we can increase this margin, the system becomes more stable. Okay. With it, we are